This is a relatively inexpensive stepping motor. This is a 24-step motor. So it's 24 steps per revolution, which is 360 degrees. So this guy only has a resolution of 15 degrees per step. So we're running this off a Arduino microcontroller, so, which is pretty neat. This program's in a language called they call these sketches, but it's very similar to a language called C+, if you ever heard about that. But you see, programming is not real easy. So what this program right here does is I'm going to enter an angle, and we'll have to go in 15-degree increments. And what we're going to see is the stepping motor is going to move that angle, but it'll do it in steps. So this is where I enter the angle I want it to go to, right here. And then the information that pops up there is really not important to y'all. So first thing I'm going to do is just tell it to move 15 degrees. So I'm going to tell it to move 15 degrees. Oops. Let me get back on the... not that one, Rich. I need this one up. And this one up. Sorry. And that's the narrowest I can make this. And that one won't minimize anymore. So let's see if we can put it right there. Okay, so this would be one step. So 15 of my watch, I'm going to start to move one step, and that's one step. Notice it moved in a watt. Moved in a step, right? Understand that. So these are 15-degree steps. I just told it a lot of degrees. Let me stop this. I don't know how many degrees it is. This is like, I don't know if y'all can see it. It's you can make it run smoother than this. Depends on how I find my camera. But right now it's moving in steps, but 15 degrees, and I entered an extremely big number. And undoubtedly in my program, I don't give it the ability to do that. So to get this thing to work, we have to start the motor at a origin point. So once we origin the point, so I'm going to try to line it up right here. And then what I'm going to do is move 90 degrees. Okay. So that would be 90 degrees. Or I can come up here and say 90 more degrees. And then I can say 90 degrees. And then, what is now, we got it lined up like this. I'm trying to get it so y'all can see that it comes back. So if I go 360 degrees, it should come back to this point right here, right? Someone tell it to go 360 degrees. Is that okay? Is that neat? Okay, I'll get y'all some. So if I tell it to go 720 degrees, it should make 2 revolutions and come back to this spot. But I don't know if you noticed, but it's moving in steps, and each step is 24 degrees. This is open loop. So I'm telling it to go 360 degrees, but I don't know it's doing that if I come over here and do this, right? You understand? So this would be open loop, but it's very, very precise if I start it from a point of origin. So if I come over here and start it right there, that's my point of origin, right? You understand? Now if I go 360 degrees, it's going to come back to that point right there. So as long as we can start these things from a point of origin, from a 0, then they're very, very accurate on position. And I say this is very, very popular in printers. Not only position the paper, so it's got a sensor in there that senses the top of the paper. You push it in there, and then from then on, if it knows where the top is, and it knows it's 11.5 inches long, then it knows exactly where it's at anywhere on that paper, right? You understand? Or anytime you turn it on, you hear that thing trying to find itself. It's got a sensor on one side, usually the left side, and it goes over and detects that sensor, and from then on, it takes that as 0, and from then on, the stepping motor is very, very reliable, unless you get a paper jam. And if you get a paper jam, once you clear it, it'll go and find itself. So these are stepping motors. They're DC motors. I got it running off a DC power supply, which y'all can't see over here. We could do it directly with the Arduino, but here we're going through a circuit, which is this circuit down through here. And that was the schematic that I put on before. So this is a real reliable place. The mobile robot that we have, that I ain't quite got going yet, it uses stepping motors to run its main drive. So we tell it to go ahead 1 foot, and it knows there's so many steps in 1 foot, right? You understand that? And it can do real well. So as long as we start it from a point, so if y'all go over here on the other side, I don't know if y'all noticed the piece of tape on the floor. That's where we start the robot at. If we start the robot there and tell it to go ahead, go ahead 15 feet and turn left, or make a 90-degree turn, then it's going to be okay, unless something gets in its way, right? Because it's an open loop system. Are we okay? So that's stepping motors. Any questions on that? So it moves in steps. Like I said, this stepping motor right here is what we call a 24-step motor. You can get these things up to, I think the biggest one I ever seen is 720 steps per revolution. And then, if it's a certain type of stepping motor, you can half step it, which means you can step it and then you can step it in the center. You know how to do that. So basically, you could get, if it's got 720 steps, that's 1,440 steps in 360 degrees. And that's pretty dang precision, right?
Steps all in order. It could go to that point. That's what you say.
No, but it's doing it in steps.
I know, but step 1 might be a 30 degree.
Well, if it's no, you have to go in the order. So if you had 360 degree steps, if you had 360 steps per revolution, that means every step would move 1 degree. And if I wanted to make 360, if I wanted to go 1 revolution, I would have to tell it 360 degrees. What this does, it's mathematically doing that. So when I come up here, and you can see that in the program, when I enter 15 degrees, it comes up there and divides it out, right? You understand? And it comes up and does it that way. So it mathematically figures the number of steps. That's what the program does. Does that make sense, Jerry?
Yeah.
So if I come up here and say 360 degrees, what it does is divide that by 15. 360 divided by 15 would be 24, and that's how many step pulses it would see.
What is that?
What do you mean? Is it out here?
Will you have that in service here?
Yeah, we got it on the carousel over on the Amatrol line. It uses a step motor.
Oh, okay. Well, that one has 3 stops.
No. You're getting stops compared to degrees. It might take 500 steps to make it go 90 degrees.
The spark comes on and it turns over to
Yeah, but you don't know how many steps it did to do that. Understand? So that would be like me entering 90 degrees right here. Well, if I enter 90 degrees, it turned 90 degrees. But how many steps was that?
Whatever 90 degrees.
Well, it's 15 degrees per step.
15.
Okay. And that's how many pulses I sent that thing to make it turn 90 degrees. So you don't go through steps. This is why it's called a stepping motor. It actually moves in steps.
But you wanted something in between there. Move you part of the group.
You mean between the step? Between, what's that? You know you're not supposed to do stuff like that.
I'll clear it. Clear the line. Purging it.
Yeah, y'all
Okay. You're talking about that huge piece of carousel.
over there, but it's used.
But the part comes in, it turns to the thing.
Yeah, but I don't know how many steps that motor. If it's a 720 step motor, then that would be a half a degree per step. So it'd have to send 180 steps to move to 90.
Buy the step.
You buy the motor with a certain number of steps.
That you get.
Yeah. Right, and that would be the resolution of the motor. So this motor right here is a 24 step motor. So that means it makes 360. If I send it 24 steps, it turns 360 degrees. If I send it one step, it turns 15 degrees. So the resolution or the accuracy would be within 15 degrees. But as long as you position your parts within that range, you're okay.
Can't go past it.
Oh yeah. What do you want to go past? How far do you want to go past? So here's 720. Okay, so that it's going to send it 48 steps, 48 pulses, and it's going to make 2 revolutions.
I like it already.
So
I didn't realize.
it's not an actuator. An actuator is a term that we use usually. A rotary actuator is usually a term that we use for actuators that can't turn past 360 degrees. Those are rotary actuators. These guys we call motors. Motors are actuators that can do what? They can turn more than 360 degrees. So yeah, I mean, I can enter any number you want to. It's just that it needs to be in multiples of 15 degrees. Yeah, so, it took that as 90.
You had one already. You want to reuse it.
Yeah, just move your position of where you wanted it to go if it wasn't within the resolution of the motor. Okay, so stepping motors. So what are stepping motors? They're DC motors that do what? And rotated steps. And the steps are very accurate. So these guys are really accurate. And we can run them open loop. Now, what advantage does open loop have over closed loop? What's the major advantage? Yeah, cheaper. The major advantage of open loop is a lot cheaper. Right? You understand that?
Yes.
So if I can use open loop, I'm going to do it open loop. If I can't do it open loop, I'll use closed loop, right? So, or you'll be one of those persons that goes out and buys a $700 phone and do nothing but go to Facebook, right? Or tweet. I wonder what else Donald Trump does with his phone besides tweet.
I got mine over.
Lesson 4, chapter 4, which is what? It's just continuing on with classifications. Some key terms that used to be in the front of the book. I think the new version don't have the key terms, and what you'll find out is we're going to have a lot more terms than they used to put in the front of the book. So Cartesian coordinated arm, this is also called rectangular or a rectangular geometric arm. A gantry robot, these are robots that are mounted on an overhead rail system so they can move in a horizontal plane. That's pretty popular. Prismatic, this is another name for what? A linear axis. Swing is robot rotation around about the base. The reach specification, this is the distance from the center of the robot's base. How far can it actually reach out? Of course, when you look at a data sheet, the reach is going to be minus on these industrial robots that we have. The tool is not mounted. The tool is not on the robot until somebody puts it on there, right? So when the manufacturer makes the robot, the reach is going to be minus the end of arm tool. You understand that? So once you attach an end of arm tool out there or an end effector out there, then that's going to increase the reach of the actual robot system. SCARA, Selective Compliant Articulated Robot Arm. This is a special type of robot. This is a cylindrical robot. Usually only has 3 axes. What's the advantage of the less axes you have? What's the advantage of a fewer axes? Yeah, it's cheaper, right? And because your control system's cheaper, and also your robot system's cheaper. So we see SCARA. SCARAs are used a lot in assembly and pick and place too. Everybody okay on work envelope? So work envelope is a volume. So it's a set of points representing the maximum and minimum reach of the robot in all directions. So this is actually going to increase the volume. Normally when we draw the envelope, we give 2 things. Our robots, what did y'all have to do? Some of y'all were there, right? The robots that we're doing this on. So y'all had to do an envelope. And what did y'all do? You should have done 2 things. You should have done this, right? And then you should have done this. And this should have ended. And then what else I wanted y'all to do? I need to add that. I needed you to do the arc too. And our arc is about like this, right? And I don't know what the inside arc would be, but it would be in here somewhere. So what you would do is once you combine these 2 things, you come up and get what we call the envelope. Does that make sense? Okay. So envelopes are drawn when you look at these data sheets, envelopes are drawn 2-dimensional. Now this was, what do they call that in drafting? A 2-dimensional drawing. Can't remember. A 2-dimensional drawing that represents a 3-dimensional shape. So you draw a top view and a side view. Isometric. I think that's right. So so these drawings have been around for years. So it's a 2-dimensional drawing that represents a 3-dimensional shape. And I think isometric, I believe that's right. Yeah. The total volume of space in which a robot arm can operate. So it's a volume, right? You understand that? We'll look at geometry, which is basically the same as the envelope, power sources, the different types of path we can do, and then, of course, the intelligence. And the basic functions of the robot arm is, number 1, is to do what? To support the tool. If you can't support the tool, it's not going to be much good, right? So I can't go over there and take that welder off the big FANUC over there and come over here and put it on that little FANUC. I could probably figure out how to mount it. I mean, I guarantee you I could, but the robot wouldn't even move. It would stall, right? Because it just don't have the payload capabilities. The main purpose of it, once we've figured out it can support the tool, then the purpose of the robot arm is to position the tool. That's its function in life. So the function in life of the robot is not to weld. The robot does not paint. The robot the end of arm tool does all that, right? You understand that? And then the robot arm does what? Position the tool. These are pretty straightforward. Three basic geometries, but this is basically kind of like another name for envelope. We have rectangular envelope, which is called a Cartesian work envelope. So what's Cartesian? X, Y, Z. So Cartesian is three-dimensional. And this is hard to draw on a two-dimensional plane. And this would be Cartesian. So Cartesian is always reference to a point of origin, right? You understand that? Now robots, we call this plane, this vertical plane, we call this Z. The left-right plane, which I'm going to say is this one, we call that Y. And then the in-out plane, they refer to that as X. And that's in robotics.
What was the first one? How would you say, the in out, the left, right? What's that?
This is in out. This is up down. Y is left, right. And Z is in out. So once we got a three-dimensional plane, then we can put a point anywhere within that plane, and we can reference it as a what? An X, a Y, and a Z. So much X, so much Y, so much Z would identify where that point's at, right? That makes sense? But if we look at this, this would be a rectangular system. Because up and down, left, right, in, out. So that would represent a rectangular system, right? That makes sense? But it's real neat. Even though we got a jointed spherical robot, we can jog it in a Cartesian plane. Which now, instead of me trying to figure out which axis to move, that's what I told y'all. I just say, I want to go X, I want to go Y, I go Z. And it's real easy to jog a robot in a Cartesian system. So every one of these robots give you the ability to jog it Cartesian. Cylindrical work cells, cylindrical work envelope is also called a cylindrical geometry. Horizontal, these robots are going to have horizontal axis.
What's that? Okay.
They're going to have horizontal joints, right? You understand that? They're not going to have a vertical joint. Their joints are going to be horizontal. That's not true. We'll see. A SCAR robot has one joint, one vertical joint, but it's a prismatic joint, straight up and down. A SCARA, Selective Compliant Articulated Robot Arm. And in robotics, articulated means it's jointed. Spherical work envelope is also called a spherical arm geometry. And this is going to have these are going to have both rotary, these are going to have a horizontal joint, at least one horizontal joint. Usually one horizontal joint and the rest are vertical joints. Are we okay? Questions? Yeah, this is just another name for what we've already talked about when they start talking about geometry. Articulated arm geometries may be used to combine what we call a SCARA arm and a jointed spherical arm. So this is going to be a very complicated arm. They've got a robot down at the trade school down in Columbiana that's got this feature. So it looks like a human. It's got two robots, 6-axis robots out here. So it can swing like this. It can move up and down. So it's got several, which would be this guy they're talking about at the bottom. SCAR robots have basically their main axis, their positional axis, are horizontal axis. Yeah, arm. Yes, it is. How they came up with that, I don't know. What do you mean elaborate? So to specific tasks. This type of robot has basically got two main functions it does, and that's assembly. You just put things together and then pick and place. Pick and place is just do what exactly what it says. It picks it up and moves it somewhere in place.
So over here on the model, with the
There's no SCAR robot, so there's no SCAR robot. It's still no SCAR robot. That's just a motor. It's not a robot. Geometers can also be identified as different coordinate systems. So rectangular, we can call that the Cartesian coordinates. Cylindrical is called cylindrical coordinates. Spherical is called polar coordinates, and jointed is called revolute coordinates. Now robots, usually when we jog the robots, when we jog the robots, and what's jogging? Yeah, manually moving it, right? You understand that? Manually moving the robot is jogging the robot. And it's called a coordinate system. So you jog it within a coordinate system. We have what they call a joint jog. Joint jog means you're responsible for jogging every axis. So the 6-axis robots, you got 6 controls over there that you're responsible for jogging every axis. Then we got what they call a whirl jog, which is this guy right here. Generically, we call it a whirl jog, but I think the Mitsubishi calls it XYZ, and I think the KUKA calls it base. But these are exactly the same thing, and this is Cartesian, which means I jog the robot, and now I move over to 3 keys instead of using 6. That's not true. We got 6, but the other one does roll pitch off for the end of the tool. So whirl jog, what we're doing is the whirl coordinate system, which is I put that in the wrong place, guys. And I can't move it, I don't think. So this is the one I should be at right here. So the robot don't call it Cartesian, they call it whirl, or they call it XYZ, which now makes sense because that's a Cartesian system. And then the KUKA calls it base. So this is a Cartesian coordinate system relative to the base of the robot. So the origin is in the center of the base. And then we have what we call a tool jog. And a tool jog is Cartesian relative to the tool center point, which is interesting. The ABB supports a cylindrical coordinate system. So we have X, Y, Z, and then we have rotate, which is pretty neat. Polar and jointed spherical, I haven't seen. As far as moving the robots, none of our robots support those, but these would be other terms that you would be able to use, right? So rectangular is called a Cartesian coordinate system. Cylindrical is called a cylindrical coordinate system. Then we have spherical, which is also called a polar coordinate system. I think about the world and the pole, when I talk about polar. And then revolute. Basically, revolute is multiple jointed robots where one joint mounts to the other, which would we call a revolute coordinate system. I think that's in the glossary. I think I put that in there.
And revolution.
Revolute.
Full circle.
But it's not revolution, it's revolute. Which is,
Anything to do with the circle.
well, yes and no. It's row rejoint. Basically, it's row rejoints that are mounted in a chain. That's what it means.
Okay.
So it's row rejoints that are mounted in a chain. And I think that's in the glossary. I need to go back and put these in there too. So like I said, this thing is definitely in flux. I should have left this open. This guy does a pretty good job with recording the videos too. So I think we have a SCAR robot in here. I know y'all get, just show y'all what it looks like. Of course, I can't find it. Of course, 12 Island Just Robots. How does it work? So this is a SCAR robot right here. So notice it's only got 2 positional axes.
What did Woodpecker do?
This guy?
No, the other.
This is a SCAR robot. This is programmed, by the way. Y'all got to understand, these were programmed. So this is a 6-axis robot. It's an Epson robot. What they're doing is they're touching their tool center points. They're making all these neat new motions. This is a SCAR robot right here.
Okay, so this really not really old.
No, it's just a demonstration. We got one video somewhere where they got a demonstration what they're doing. And this is a rectangular robot. Can y'all see it down here? I don't know what I just did yet. So these are 3 different, so this is a rectangular geometry or Cartesian. So the only thing you can do is, here's the tool mount right here. Y'all see it? And you can move this in and out. You can go this way, right? So this would be Cartesian. This is a SCAR robot, which is a cylindrical robot, jointed cylindrical. But see, it's only got 2 positional axes. It's got this one back here, and it's got this one right here, and then it's got 1 prismatic axis, which is the one that's controlling the tool. So we're talking about 3 axes that can do what this robot could do. So now it's got, now this is the tool center point down here. I don't know if y'all can see it. And this robot here is actually, they're running together. This is simulating a assembly robot, and why it blanks out, I don't know. But that's a SCAR robot. It's that horizontally axis. So usually a SCAR robot is a 3-axis robot. 2 positional axis and then 1 orientation axis. And but it's only 1 orientation axis, and it's a prismatic or a vertical axis or linear axis. Well, those things can scream. Those are probably the fastest ones you'll see.
Talking about just so they can show you how accurate they can stay together.
Oh yeah, so they each had something in their gripper or their attached to them, and they were literally moving together, keeping their tool center point together.
But they weren't running the same program.
They were separate programs. So they took some, well, yeah, but it can be done. They used to have 2 robots, 2 ABB robots up in the McWayne Center. I think it was up on the 3rd floor that was running synchronization. I think one of them was holding a bunch of, I can't remember, one of them was holding a bunch of Coca-Cola cans or something, and the robot was going between it, and they was flipping them around. It was a really neat thing. So classification by coordinate system. So the one on the left would be a Cartesian coordinate system, but it would have a rectangular envelope or a rectangular geometry. This guy would be a cylindrical. So this guy, it would be a cylindrical geometry, and that's the same also on the envelope, right? Or it would be called a cylindrical coordinated robot. This guy right here, what can it do? It can rotate, it can move it out, but as soon as I add this tilt, then that's going to be spherical, right? You understand that? So this is a spherical robot, also called a polar coordinated robot. And then we have this guy right here, which adds multiple joints. So what we've added now is we've added a second axis. So now this would be revolute, right? And so jointed spherical geometry, which would be called a revolute coordinate system. Are we okay? We're okay? And this was on the test. So this is where we got a little ahead of ourselves. Like I said, that was actually a extra credit on the test. So what we do is we have R is going to represent how many rotational axes the robot has. P is going to represent the number of prismatic, which is linear axes. So if you looked up prismatic, that's what it says. It says something that it says a joint or an axis that moves in a straight line.
Do you know where that is? Well, sorry.
In the book?
Yeah.
Oh, I don't know.
That's fine. I'll find it.
It's in chapter 4. So a robot that was classified as a 3P robot, that would have what? 3P, so that means 3 prismatic, so that would have 3 linear axes. So that would be rectangular, right? An R2P, also called an RPP, would have 1 rotary and 2 prismatic. Okay? A 2RP, or also called an RRP, would be called a 2 rotary and 1 prismatic. So that was the SCAR robot that we were looking at. And then a jointed spherical, this guy here has 3 R's. Ours would be what? What would ours be? These industrial robots over here, what would they be? How would they be classified? No, according to RRP, what we're doing at now. So what we're doing right now is we're talking about the classification according to the axis. Well, 3R would only mean it's got 3 axes. Ours has 6. So our robots would be called they're classified as 6R robots. Understand?
You know,
I did. That's only if we understand at the end. We don't have to understand at the beginning, but at the end.
so it ain't even on there what we have. That's
What do you mean?
It's not an option. It's saying 6R.
It's just because I didn't put it on there. Because I asked the question. I'm the one that made this one. So yeah, ours would be 6R. In fact, all the robots, the Mitsubishi would be a 5R robot over on the Festo line. The Fanuc, let's see, not the Fanuc. All the robots we have are 6-axis or 5-axis. They're all R's. They don't have any T's. So we don't have any prismatic. I wish we could get a SCAR robot, but we're lucky to have the robots that we have. These average, by the way, the average cost for these robots over here is $50,000. Huh? 50.
Was they donated?
No, the only one that was donated was the big Fanuc. So everything except for the 2 big Fanucs, everything in this robot was bought with grants. State didn't buy it or anything. Well, that's not true. State of Alabama has what they call a workforce development grant, and we got that to buy these robots right here. So we can't afford right now. We can't afford a $50,000 SCAR robot, which would be nice. We got a company down called Technical Training Aids that has a Delta robot that they brought up, and and they keep it in storage all the time. We tried to get them to leave it here, but they wouldn't.
What was that?
It's called a Delta robot. We'll see those. So a Cartesian's got to have at least 3 linear axes, right? Because it's got to move back and forth, in and out, and up and down. Also uses pick and place, primary use in material handling, machine tending, and resistance welding. Do y'all understand those terms? A lot of people call these spot welders. That big old welder over there is a spot welder, but it welds, so it depends on the resistance of the metal. So, what's the formula? P is equal to, one of our formulas is I square R for calculating power. And what a resistive welder does is it literally comes in here and pinches two metals together. And then it puts enough current through that to cause those things to melt together. It works real well. But just think about the amount of power. Because how much resistance is it working into? People think that metals have no resistance, but they do. So if I can put enough current through a chunk of metal, I can melt it. And that's the way, and this is why they're called resistance welding, because what they're doing is they're putting a lot of R, they're putting a lot of I through the R of the metals. And they literally just pinch the metals together and put all that current through there. So that's why when you go over there and look at that resistance welder on the big Fanuc robot, that's why it's got all that dang copper on there and those big old weld heads. And it got, that's right. Yeah. You don't do a resistant. Yeah, you got to pinch it. Resistant welder, you got to pinch. You got to pinch what you want to weld in between them. Right. And that's they call it. Huh?
But I not with the resistance, no. I hope so.
So this is predominantly what they do to, no gases.
No use of wire.
Normally they're water cooled because of the amount of heat they generate. And
that's common in welding anyway.
Yes. And but it takes a lot of current to do a resistive welder. So that's where it comes in. So all the sheet metal on your car is put on there by a resistive welder, if it's not hand weld.
You know what they use
I would imagine they probably use 660, but you got to understand, going to the welder is probably maybe 2-3 volts. Extremely low voltage, extremely high current. But remember, that's the amps that do it. You don't want Cartesian advantages: simple geometry and control system, very large work envelopes, can easily be overhead mounted. So this is a Cartesian welder that if I can find it real quick, guys. This is machine tinning. This is actually doing an injection molding machine. Plastipack makes the plastic bottles that everything comes. They make I don't forgot what they call them. They look like beakers that they can send out to companies, and then they expand them down there too. Cylindrical geometry, swing. Guys, I would really appreciate y'all if y'all don't carry on conversations while I'm up here talking. If y'all want to carry on a conversation, I'd appreciate it if you just get up and go out in the hall out there and y'all can talk about whatever y'all want to talk about. I know it bothers me, so I guarantee it bothers the people that's trying to sit in front of you. So, huh?
I can't hear you.
Don't bother Jerry. Jerry can't hear you anyway. So that's why I talk so loud all the way. Jerry's got this little thing he sets up every once in a while, but the batteries don't last very long. So swing, rotation about the axis, reach is the distance from the center of the robot's base to the furthest point in the vertical horizontal plane. But when they give the reach specification inside the data sheets, that's minus the end of arm tool, right? Y'all understand that?
Say again, sorry.
When they give a reach specification inside the data sheet, that's minus the end of arm tool.
Okay.
Unless the end of arm tool is permanently attached to the robot when it's, yeah. So most of your industrial robots don't come with the tool. So as far as I know, Yaskawa might do tools. Yaskawa is a big control company over in Japan. They make the Motoman robot. So they might make end of arm tools. I'm not sure. But I know Fanuc doesn't make end of arm tools. ABB don't make them, and Kuka don't make them. And they sell the robot. Now they might sell it to a company called Lincoln. Y'all ever heard of Lincoln? Lincoln makes welders. So if you ever went to Lincoln, you'd see a ton of Fanuc robots up there. And so Lincoln attaches an end of arm tool to it, and then they sell that robot work cell to their customers. But still, if you look at the specification for the robot, it's not going to include that tool, right? You understand that? I don't know what it is. And that's what's nice about these guys. They have one basic function in life after supporting the tool, and they position the tool. So if you see on a test, it says, what's the main function of the robot arm? What you're going to put? What you're going to select? To position the tool. And what's the function of the tool? To do the job, right? So this is a SCAR robot, Selective Compliant Articulated Robot Arm. And this is one of those terms that I think they came up with the acronym and then made something that fit it. I'm not sure. So what's an acronym, by the way? Right. So it's a word that's made up from a phrase, and what you do is you just use the first letter of every pertinent word. So a lot of times they'll include the fours and the V's and stuff like that if it makes sense. But over time, it basically that's what an acronym literally is. It has to make a word, but over time we repeat letters and we call them acronyms. NASCAR is an acronym. But then we come along and say SEC is an acronym too, even though it's not a word, we just repeat the letters, right? So over time in computers, we got so many phrases in computers where we use acronyms that eventually they just started saying letters. But to be a true acronym, it's got to make a word like SCARA. So very few people call the SEC sick, right? This is a SCAR robot. The SCAR robot, how many rotary axes does it have? Two, and those are positional axes. And then how many? Then the orientation axis, it's got one, and that would be this linear axis right here. Only 3 axes. And this guy can scream. It's one of the cheaper robots that we can buy, but it's limited to what it could do. It wouldn't weld, right? You understand that? But as far as assembly, putting things together, so what they're putting together is down here, and it's going over there picking up parts and sticking them where they go. This guy right here is very, very, very popular. Sometimes they add another axis out here where they can rotate that. So
I can't read what's
Adapt. Now I hadn't heard of Adapt before. That might be the company that sells it. You know, when you buy stuff, you can put what you want to on. It's just like when you go out and buy a car, you can take Ford off of it if you want to, right? Or take who you bought it from. That's usually one of the first things I do, especially now that most of them use tape. It is, and like I said, these guys right here scream. We got one video. I'd have to find it. I'll see if I can find it when we take our break. Where it's just moving. They got a suction cup out there, and it's just moving balls around. It's deep. I mean, it just flies.
Where is that?
It's a video that I've got somewhere out there. Okay, guys, you'll go ahead and take another 10-minute break. So y'all know what a SCAR robot is now, right? This is another video of a SCAR robot. So this is just a demonstration. So these guys are used a lot in pick and place. Like I said, a couple things because of their simplicity. Because you only need 3 axes, right? You understand? If you don't add rotation to the tool center. So what is the tool center point?
Center point.
Yeah, what is a tool center point? Not necessarily this tool center point.
When the action, have to use the
Yeah, it don't have to even be part of the tool, right? You understand? So where would we want the tool center point to be on our gripper? It wouldn't be on the gripper, it would be in the center of the gripper. That's what we're trying to position, right? You understand that? So if I taught a tool center point, that's where I would teach it at. By default, your tool center point is set in the middle of the mounting plane. The middle of the mounting plane. So this would be a cylindrical robot. This is not necessarily a SCAR robot. So this is a cylindrical robot because it don't have what? It don't have tilt. Is this the same figure? Is this figure in your book? 4.4? In your book? This is the second version of this book that we bought, and they've changed some things. So I just want to make sure.
Yeah.
So this would be a multi-jointed spherical robot because look, it's basically got a rotary joint here. It's got a rotary joint here. It's got a rotary joint there. So this would not be what we call a SCAR robot. Go up and down. But it still would generate, overall it would generate a sphere, right?
And the joints are called rotary and linear.
Prismatic.
Prismatic outlet.
Right, when they specify them in a spec sheet, they call them prismatic. So prismatic is a linear axis. Linear means in a straight line, so the term linear does not necessarily mean prismatic. Does that make sense? Yeah, because that's the only joints we can have. Y'all understand that? That's the only axis we can have. They're either going to be rotary or they're going to be what? Prismatic. Or linear. Cylindrical, these are the advantages, there's quite a few. Y'all can read those as good as I can. Can't y'all? You want me to read them too? Good horizontal reach, vertical structure, reduced floor space, got a large payload. Rigid structures produce good repeatability. Small mass. And of course, the technical limitations of the axis. Are we okay? The cylindrical geometry is primarily used for machine canning. Y'all understand what machine canning is, right? What is machine canning? Moving stuff between machines. So one of the videos we showed, the machine canning robot, was the robot that was moving the cams between the car cams between different milling machines or lathes. Assembly, material handling, palletizing, arc welding. We can use these arc welding, adhesive bonding, sealing, grinding, deburring. So this guy here has a wide range of uses. Spherical arms, at least a 2RP. These were one of the first ones to be used in the industry, right? We don't see many of these today because they only got that 2 rotary exit and 1 prick. So all they can do is this. They can do this and they can do this, and that's all they can do. They don't do it back here. They actually has a prismatic axis that moves back and forth, right? I can't tell you the last time I saw one of these, but these were the first guys that went into production, right? I mean, went into manufacture with these 2RP robots. So this is a spherical geometry. All right. Are we okay? These are the advantages and disadvantages of a spherical. take up a lot of spore space. And it don't have enough joints, which means it doesn't have flexibility. Are we okay? Primary for spherical is machine cleaning, material handling, welding, and painting and coating. I think this is right out of the textbook. But then we have jointed sphericals, also called a polar coordinate system. So this is the 200 ID, I think an ID. I think that's an IC, right? Yeah, that's a 200 IC. The 200 ID, they look a lot alike, except the way the joints are made up is, that's what we have on the Amatro line over there. These guys are highly flexible. They're very general purpose. They can be basically mounted a tool depending on what you need to do. Articulated, and what that means is articulated means these are basically it means vertical joints that are chained to get put together in a chain. So we got this guy here, we got this guy here, it's chained to that one, and that's when we use the term articulated in robots, that's what they mean. Vertically articulated. The link together.
Oh,
Go ahead.
okay, you just call it a chain, so like a chain.
That's exactly what it goes to links, but here the links are joints. And that's what we mean by in robotics when we use the term articulated. Of course, usually when we talk about an articulated person, we're talking about they're very precise, right? In robots, what we mean is it's multiple joints in a chain. These are 3R robots. These are positional, and then the number of orientation axis you have depends on the robot. Ours have 3 positional axis and 3 orientation axis, right? Except for the Mitsubishi, it's got 2 orientation axes. And that's why this note is out here. It doesn't mean it can't have more, but to be this, it's got to have at least 3 what? Positional axis. 3 positional axes. Don't understand the difference now, right? So these are my positional axes. My positional axis is my shoulder and my elbow. That's my positional axis.
It says, it has the left and right moves are by the base. It says in the book here.
Yeah.
Left and right moves are provided by the base. So the base is like on something.
We call this guy right here, the base, basic of the robot is what? We call this the base joint.
Right.
Okay. So we call, well, yeah, but technically the base is what we mount the robot with. Well, we call it it's called the base joint because the base has a joint at the top of it. That makes sense? 3R, well, it's not necessary as a 3R, but you got to look at this right here. So that would be 1, right? This right here would be 2. This would be 3. Those are your 3 positional axes. This right here is 4. This right here is 5, and this right here is 6. Those are not what they're talking about here. They're saying it needs to have 3 positional axes. How many orientation axes can it have? Probably at least 1. Yeah, it's got 6. It's a 6-axis robot. This is what we have. These are 6-axis robots. So they're 6R robots, but what they're talking about here is the number of what? Positional. That's why it's very important that you understand the difference between positional axis and the orientation axis. So these are my positional axes right here. These are my orientation axes right here. So what am I doing now? I'm not moving my arm, I'm moving my hand. So what you got to do is picture your arm being two parts. This is the robot, this is the tool. So what am I doing here? I'm moving my whole arm, right? You understand that? Those are my positional axes. These are my orientation axes. Now I'm not moving my arm, I'm only moving my hand, right? You understand? So your positional axes are the ones that move the robot. Your orientation axis are what moves the tool into the position you want it to be.
You don't have 5 markers. 5 would be.
Yeah, I just said, I said it, but I didn't write it in.
Where it's fitting, right?
Yeah, that 5. In fact, that's not even the right place. 5 should have been right here.
That's 5, yeah. But then 6 is rotate.
We can't do that. So this is 4 right here. And this is 5 right here. And we don't have a 6. 6 would be rotating right here. We can't rotate our wrist. A lot of people think you can, but you can't. But if you clamp your hand down, you can't do anything with it. So we rotate back here, which is exactly what axis 4 does. So axis 4 rotates at here. So the Mitsubishi robot does not have an axis 4, but it does have an axis 6. So it's going to have some problems, but that's all it needs. And what did I say? What's it? The fewer the axis, the cheaper the system, right? You understand that? The more the axis, the more expensive the system. By the way, on the new Festo lines, they got a Fanuc robot on. We got a Mitsubishi. Selective Compliance Articulated Robot Arm, a SCARA arm. Sweeping motion, horizontal in and out, vertical movement gripper, vertical moving, produces a cylindrical envelope. And these guys are predominantly used for pick and place and assembly. Instead of fast. Deep horizontal reach, minimum floor space, high position mobility, end of arm, precise vertical alignment programming. It says complex controller, but the controller is a lot more expensive than a 6-axis controller, right? So compared to the other robots that we use, this guy here would be relatively inexpensive compared to a 6-axis robot. So this would be a SCARA robot. This guy's got 1, 2, 3, 4 rotary axes. And of course, all our robots are jointed spherical arm geometries, also called Revolute coordinate system. So what we do, we got a base, we have what we call a shoulder, and we have what we call an elbow. You okay back here? These are our positional axes. The orientation axis, I don't know what we call it. We call it the wrist, but basically we got 3 movements. We can rotate the wrist and we can tilt the wrist, right? Currently, one of the most popular configurations. So what the biggest advantage of this guy is its flexibility. We can basically do anything with that 6-axis robot on there that we can do with our arm. And if we add additional axis, we can do. So if I was to lay down on my side, anything that I can do like this, that's what this guy can do. And then we add these axes, we got all this stuff, right? You understand? So we can basically position our tool anywhere you can position your arm. But, so their biggest disadvantage is their flexibility. So all these other robots we talked about, the cylindrical robots, the rectangular robots, the SCARA robots, we can program this guy to do what those guys do. And the biggest problem, of course, is the cost. The biggest advantage is the flexibility. The biggest is the cost. So the robots that we looked at for a size, this guy here would be the most more expensive, more complicated controller. Envelope close to a perfect sphere, currently one of the most popular configurations, matches the movement of the human arm. Now, I don't have a hand, but we can make up for the hand. We don't have that. But what can we do with this hand? We grip stuff. So we can grip stuff with a gripper, or we can mount a permanent tool on it. It's going to have one function like a welder, and we're not going to put a gripper to hold a welder, right? You understand? We'll put a welder out there. If I'm using it to drill holes, we're not going to put a gripper to hold a drill. We're just going to go ahead and mount a drill out there. So this is a 6-axis robot. Y'all know the axis numbers now, right? Start at the base. Go 1, 2, 3, 4, 5, 6 for a 6-axis robot. And all of them give them this numbers. I think the FANUC calls them joints. So if you looked at the jogging keys, they're called J1, J2, J3, J5. The Cuckoo calls them axes. So the jogging keys are called X1, X2, X3, X4, X5. The Motor Man, and I don't know where they came up with it. They call theirs ULS something and something. How they came up with those letters, I don't have the slightest idea. And I have tried to find them. The ABB, they don't call them J's or stuff like that. They just number them 1, 2, 3, 4, 5, 6. I'm going to jog that robot. Are we okay? So these are the most flexible robots out there. These guys, they're all over the place. If you went down to Mercedes and went through their paint shop, if you went through their assembly plant or anything like that, these are the guys you're going to see. If you went down to Plastipack or Plastech, they're going to have a bunch of rectangular coordinate system robots because they come in on top of, they use the overhead rail system, and they come on top and just unload those machines. So it depends on where you got, which ones they got. By far, these are the most popular. And these are the advantages. So the biggest disadvantage of this thing is the complexity of it. So, you know, the controller's got to be more complex because it's running 6 axes. It's got to monitor sensors. It's got to monitor the servo motors out there. It's got to keep up with it, where everything's at, all the speed, all the position. So it has more demand than you, right? So like I said, in this class, we'll look at some programming. We'll go over there and we'll play around with these, but I'll do it. But we'll teach a program over here before long, let y'all see what we do over there. And basic teaching points is not hard. It's when you come in and do that other stuff. These guys, the list would go on and on and on. What you got to understand, anything you position with your hand and you do with your hand, this robot can do. What can y'all do? Can y'all use a screwdriver? Well, we can let the robot do that. It can tighten stuff down. It can do wrenches, it tightens bolts down. If you can weld, we can make these things weld. If you can paint, we can make these things paint. They got one robot. I'd like to see that programming where you come in and you sit in front of a camera and the thing picks up a pen and draws you. That's an interesting program. So it can do stuff like that. The only limitations of this thing, of course, is what your tool, what you put out there, and then how good you are at programming. So this list can go on: assembly, coding, painting, welding, machine tending, milling, material handling, palletizing, Coatings, of course, that's on there. So anything just about we can do with our human hands, we can have one of these robots do this. Gantry robot. This is a robot mounted onto an overhead system that allows movement across a horizontal plane. And I think I showed y'all the video of the rectangular robot that was called a gantry robot. And
If you like brand name.
no, gantry is a name that's been around for years. When we worked on and the name has changed from what I learned it. Out of U.S. Steel, we had gantry cranes. We had overhead cranes, and we had gantry cranes. Gantry cranes, at the time, what they did is they had rails down on the ground, and then the crane had a big old thing, and then the operator set up here, and so it was actually on a rail system on the ground. In robotics, a gantry crane is just a crane that's mounted over, a robot that's mounted overhead on a rail system that allows it to move. So just mounting it overhead does not make it a gantry robot. So when a gantry robot, we're going to take it and mount it to something that has the ability to move the entire robot. A lot of times and it could actually be a combination of a rectangular robot with a jointed spherical robot mounted on it, which is what they're showing here. So notice this robot, we've added a linear axis up here. So the robot can not only move up, it's a 6-axis robot, it looks like. It can also move back and forth. But I've seen these things, very extensive systems where, now what's nice about a gantry robot is how much floor space does it occupy? None. Yeah, they had one at Bridgestone moving tires around, and it was a gantry robot. You don't occupy any floor space. So in robotics, so if you got out in industry, a gantry robot is a crane that's mounted on rails that's on the ground. But in robotics, the term gantry robot is a robot that's mounted on an overhead system that allows movements across a horizontal plane. So just mounting a robot on the ceiling does not make it a gantry robot. Some of these robots can be mounted all kind of ways. So that's one thing that you need to understand is that if you go out and buy a robot, it's not designed to be mounted on the wall. If you mount it on the wall, then odds are you're going to sacrifice the repeatability of the robot, right? This is the Delta robot. Can you see how I got the name? Well, if you look at the Greek, this is the symbol for Delta. So if you look right here, you see that same thing right there, and that's why this got the name Delta robot. These are overhead robots. They could be gantry robots, but these are always mounted overhead, and they're used primarily for pick and place. And these guys right here are really, really neat. Let's see if I got a. In fact, we could probably just go to YouTube and find a Delta robot. Call it a spider robot. These guys are used primarily. Thing over now. Ground. Do it. To the controller. The suction cup to me.
Oh.
The poplar. Yeah, so it looks like it's
Pretty good.
made. You know, back in the 60s, you couldn't get 100,000 miles. If you got 100,000 miles out of a car, you got to join what we call a 100,000 mile club.
Wasn't because it was
Of the
good.
precision.
Odometer didn't go from 99. I thought a car was 70,000 miles. I didn't know it was 200.
No, why you couldn't get 100,000 miles on a car? Because it fell apart.
Yeah.
Okay, so when we talk about reliability, you know, you need to understand how it's manufactured. I've seen people make Delta robots out of not injection molded out of 3D printers. They literally print the arm and stepping motors. So,
You know, I had a packer water.
no,
That thing moves around all over the place.
well, that was basically a rectangular robot.
Don't have it.
5 powers. Hydraulic, pneumatic, and electric. We already learned some things about these. What is hydraulic?
It's powered by,
Yeah, it creates pressure by a liquid. What's pneumatic? Yeah, by a gas. So there are some pneumatic systems out there that does not use air. They use other forms of gas. And then electric. Which one do you think's the most widely used? By far. Why? Oh yeah. Electric's all over the place. Yeah, I mean, we don't have to generate electricity. We can just tap into that. It's generated for us, right? You understand that? If I use hydraulic and pneumatic, that's not generated for us. So I've got to have a hydraulic system that makes that pressure, or I've got to have a pneumatic system that makes that pressure. So hydraulic systems, this is what we require. We got to have a tank that does what? Oh, we got to have a pump that does what? Well, creates the pressure. Good. Got to have piping. What's the piping? Routes the fluid not only to the actuator, but also we have to bring it what? Back. Control devices. Yeah, we got to control that pressure. We're going to have to control the direction. If I want to make something go left or go right, we're going to have to reroute the direction of the fluid. We call those directional control valves. And if I want to control how fast it goes, then I got to control the flow rate. So we have flow control valves. What do the flow control valves do? They control the speed. Directional control valves can control the direction of the fluid. And then, of course, pressure controls how much pressure we apply. If you don't apply enough pressure, it's not going to be able to generate the required force. Right? You understand? If you generate too much, then it's going to probably bust seals and all kinds of stuff. Two types of actuators are linear actuators and rotary actuators. So if you take the fluid power class, you'll get to see linear actuators are real easy to understand. Rotary actuators are just are fluid power motors. Very high power to size ratio. That's what we looked at, right? You understand? Because as the pressure goes up, the size of our actuators do what? Go down, right? You understand that? Can be used in explosive environments. Disadvantage is we got all the time, we got what? Such high pressure, yeah. You very seldom get into a hydraulic system that's been around for a while that don't leak. Most of the fluids they use in industry are oils. What's the advantage of oils? Yeah, they lubricate when they go through there. You got all these directional control valves and actuators. Anytime when you move surfaces against something, you have to have
all the pipe bills.
Yeah, there are some systems running water as their hydraulic fluid, but usually they put a little oil in there. Yeah.
Looks like milk.
Yeah, looks like milk. Yeah.
That's the fire.
We got to have a pump, so usually our pumps are electric pumps. So we got to take that and take electrical engineering and convert it to hydraulic power, right? Hydraulic robots are very noisy. And we can get, we're probably this year we're going to look at getting a small hydraulic robot, like these little plastic ones over here. They're pretty cheap, so we can afford those, just so you can see a hydraulic robot.
You gotta have all those pumps.
Well, yeah, but these work on you, so you're the pump on our hydraulic. So when you move a lever, it generates the pressure. So it's a pretty cheap setup. But we can use hydraulic. What's nice about hydraulics is that it don't generate sparks. So we still use these in applications that's in explosive environments. Pneumatics. What do we require in pneumatics? We still normally, if it's not what we call a continuous flow compressor, which are very, very expensive, then what we do is we have an intermediate duty compressor motor, and we store up pressure in a tank. So we still usually in most pneumatic systems you have a tank. I'm sorry, this is still. And plus, if we're using air as our gas, air has water in it. And when you compress it, it releases that water. So that means we need to have some system. If we're going to have a good system, we need to have some system to get rid of that water. So a good compressor will have a water removal system on it. The compressor we have in this shop is really good at that. The compressor they have over in the Mill South in the fluid power class is very, very crummy. So we went in there one time to teach that class, and there was nothing but water that came out. So somebody hadn't. And if we're using some of your actuators require lubrication, so we have to have an oil ejection system. So we've got two robots over here that don't use self-lubricating valves, and that's the ADV and that's the motor main. And every once in a while they stop working. We have to take the valve apart and do what? We have to lubricate. We do have some oilers, we just haven't got them into place yet. That's one of my projects. So, advantages, pressurized air is usually readily available in most plants, low cost, well understood technology. Fast operation, these are ideal for gripper controls. The big advantage is the cost of the system, right? We have two things is number one, we're at a lot lower pressure, which means the whole system, now I can have valves that's made out of plastic, or I can have valves that's made out of aluminum. Right? You understand that? My tubing, I can use plastic for tubing. Right? Instead of metal. So in hydraulics, 90% of your tubing is metal. The only time you'll see this a high pressure tubing is when we go to something that's in motion. So your air conditioning system in your car is basically a hydraulic system. And 90% of the tubing is metal. The only place you have high pressure tubing, flexible tubing, is that runs to your compressor, right? Because your motor shakes all the time. Very expensive. We do have problems controlling the flow rate. When in doubt, meter out. And of course, limited payload. Are we okay? This is probably by far the most widely used power source for the end-of-arm tool. Electric power used as the primary power source for most hydraulic and pneumatic systems. A few hydraulic systems use internal combustion motors. So I have a pressure washer. What does it use? It uses a combustion motor. It would be a hydraulic system. But you can buy them electric. You can buy electric cars. But no matter what your power source that moves your actuators, your controller is going to use electric power because it's a computer. Y'all understand that? Servo stepper motors, we looked at that. What's a servo motor?
High-tech
Closed
loop.
Yeah, it's a motor that provides feedback. So all these robots have servo motors. Great for rotary drives, rack and pinion, and ball. What's a rack and pinion? A rack and pinion is something that takes a rotary motion and converts it into a linear motion, or something that takes a linear motion and converts it into a rotary. So basically it consists of a linear gear, and then it's got a rotary gear that matches with that. Feel like my gear. And that's rack and pinion. So if this gear turns, it's going to move this linear gear back and forth, right? Or we can move the linear gear back and forth and move a rotary gear. So a rack and pinion is a system of gears that converts a what? A rotary motion into a linear motion, or vice versa. So we got some rack and pinions over there. Are we okay? Drive can be either DC or AC. What does DC stand for? But what does it mean?
Battery.
What does it mean? Well, if we said DC meant a battery, then I might as well just throw my car away, right? Yeah, it's flowing one direction. Yeah, we don't have any batteries in our TDs, and they work off DC. We don't have any. We do have batteries. Anyway, so DC is direct current, and AC is what we call alternating current. So alternating current is a current that's constantly changing direction, but it does it at a constant rate. Depends on where you're at. The two main rates are over here. We use 60 cycles per second. A lot of places in Europe, down in Africa and South America, they use 50. Some countries use 50 or 60 in different locations within the country, which is pretty interesting. The biggest advantage of AC is that it's very efficient to transmit. The biggest advantage of DC is we can electronically control it. So anything that's electronically controlled is going to be DC. So this computer operates off DC. These computers operate off DC. They have a unit in there called we call them power supplies, but they're AC to DC converters that takes the power company's power and converts it over to DC so we can electronically control it. Which is that's one. Not electronic, that's not electronic control, that's electromagnetic. And also AC motors are cheaper than DC motors too, so. So, what type of motors are in that robot over there? They're DC motors, right? Yeah, because we're trying to control them precisely. We're trying to electronically control those motors. The controller works off DC. All the sensors work off DC because they're electronic devices. No energy. We don't have to do the energy conversion unless you got a generator at your house. Operating noise levels are low. Direct drive models provide very quick response. Payloads capable of limited around 300 pounds or less. Operational in an explosive environment could cause you problems. Electric sparks are not good in a gaseous environment. But we can't, well, that's not true. We can't directly, when they say 300 pounds, they're talking about basically direct drive type situations. We can run an electric motor through a gearbox and basically do what we need to do. They've got, I think they're, I forgot what they were, single phase, I forgot what size they are, motors moving one of the big dome covers out there. But they run through a big old gear train or gearbox, right? You understand that? So gears are great, but you got to sacrifice something. So if you get more torque, you sacrifice speed in a gearbox. If you get more speed, you sacrifice torque. Power in equals power out. Energy in equals energy out, right? This is we have two types of programming ways we can program robots. And I'll have to, that's probably the next class, I'll show you this. We can do what we call a continuous path robot, or we can do what we call point-to-point programming. And this depends on the robot and depends on basically the control. So continuous path, let's see how it's laid out in the textbook. So continuous path, what we would do is, while you're moving the robot, so a continuous path robot, you physically move it how you want it to go. So you go out and you put the robot in what we call a float situation, and then you go over there and you literally grab that robot and you move the robot through the path that you want it to follow. And what the controller does is it constantly records these individual little points along the way. So the speed of your motion and the direction of your motion determines how these points are recorded. So the operator physically moves the robot through its path. In the Lego robot right here, we can program it to be a continuous path robot. So so this is continuous path programming. I just downloaded this video. I couldn't find the one I had before, which was really neat. Yeah, so that's what a continuous path.
What
Huh?
intention?
Yeah, and that's, and what would be some of the problems with these? Of course, first of all, whoever's doing this has to be a skill. So if you're doing a continuous path robot that's doing welding or burring, then you're going to have a very skilled person that knows how to do it, what sequence to do it in, and how to do it, and what depth to do it, and all that other kind of garbage, right? You understand that? And what if the guy screwed up? So let's say, what if he didn't want that little dip in there? What do you think he would have to do? He'd have to redo the whole program.
But it didn't matter in this case.
No, it didn't matter in this case, but in real life it might be. So you're up here and you're moving the robot up, and you go to the right, and you say, oh, I screwed up, I was supposed to go to the left. Well, what would they have to do? Well, they'd have to move the robot back to its point of origin, and they would have to reteach the whole program. So continuous path robots look cool, but the problem is that the controller is very complex because it's got to go out there and remember all of these points. So it's got to remember hundreds of points along that path. So it's not actually remembering the path, it's remembering points along that path. Continuous path. And we can do this one. I'll have to go back and figure it out. My battery was dead too, so I'll have to show y'all that next class. This is a little robot car, and we can set this up to program it continuous path. So what we'll do next class is we'll come over here and just tell it to record it, and then we'll move it around, and then we'll come back and do what? Let it run. So we'll manually roll. We can do this real easy because of the gears. We tried to do it on one of the other robots, but the gear ratio was so high, the tires just slid. This one's got a real low gear ratio on it. It's got a small gear turning a big gear. I'm sorry, it's got a big gear turning a small gear, so this decreases torque but increases speed. So we can turn the motor backwards real easy. So right now it's charging. Yeah, when I realized I was going to teach this, I went and got it and it told me that my battery was dead. Are you leaving, Morris? You're going to let me know, right, when you leave? Okay, that's in the syllabus. That's in the syllabus. That's fine. All you need to say, I need to go. All right, you're welcome. Thank you. You're welcome. Yeah, that's in the syllabus because that could give us problems, right, if we have to have an evacuation. Assuming should feature the exact motion of the operator can be captured by the robot controller. Program length is specified in minutes of recording time instead of the number of program points. Usually not possible to do what? Be hard to edit because you'd have to get back to that exact same point, right? You understand that? The programming is commonly stored on a magnetic media such as cassette or DS&S. Cassettes are not, this is probably old. I ain't seen a cassette used. Some of y'all probably know what a cassette is. Huh?
That was done at a certain speed.
Yeah, it's recorded.
After you caught it, can you reset the speed?
Sometimes you can, sometimes you can't. It depends on the controller. Sometimes what you do is you record it at a speed, and then you record it at a percentage of the speed, and then you can change the percentage. Does that make sense?
Something simple like that. You pick it in place more to it fast.
Right. Well, yeah. Well, he could do it fast, but you can't be any faster. You can't do it any faster than the operator that I remember.
That's what it is.
This is a point-to-point programming. So what you do is you come in and you jog the robot to a point, and then you tell the controller to memorize the point, or tell the program to memorize the point. Then you'd move it and you do this one. And then what you do is tell the controller how to move to this point, and we'll look at that when we go over there. So notice on this one, they have a curve here. And up here, they have a curve right here. Well, this gives you an indication that we can't do that, and we can do that with a point-to-point robot. It's just how we tell it to go between points. So this is kind of misleading in that it looks like I can't tell it to do this, and I can't tell it to do that, but we can tell it to do that. We can. What we would do is we would teach a point there and teach a point there, and we'd teach this point right here, and then we would tell that, we call it round off. We tell the controller how much to round that off. So using point, huh?
In degrees?
No, we just put a percentage. And sometimes you have to play around with it. But we can make a point-to-point robot follow any path we want it to follow. It just takes a little more inventive measurements to do it.
Well, sometimes you might need to do that. With something.
Well, you can, but it depends on what you're doing. So, you know, if I and one of the paths when you get into operation and programming, we're going to make it follow that path right there. And these are point-to-point robots, and you're going to make it follow that path. You can do it. It's just that, and it's not as hard as it seems once you get the technique down. But what you do is you teach points, and then you tell it how to round the points. How to round. We call it round off. Yes. Mitsubishi calls it the Motorman calls it a position level. So if you have a position level of 0, it will hit the point. If you put a position level of 1, it would round it a little bit more, all the way up to 10. ABB calls them zones. So a zone 0 would hit the point, a zone 1, and then FANUC calls it a continuous. It's not a continuous robot. They call it a continuous motion. And it can be anywhere from 0 to 100% of round off. So this would give us an indication, but we still do the same thing. What we do is we just jog the robot to a position, and then we tell it then we teach a point. But when we teach the point, we tell it how to move from the previous point. Does that make sense? So here, this program right here would be made up of 4 points. According to this, we're teaching you in this direction right here. So we'll go over there, and I'll teach a program, and you'll see how it's done. It's not hard. And then we'll try to show y'all round off if we have enough time. Are we okay? Directional buttons are joysticks. So the only one that has a joystick on here is the ABB. All the rest of them we use directional buttons. Axis moves at a speed proportional to the length of the move, always moves in a straight line. We call these control path moves. And this is not exactly true. This is in the book. We have 2 control path moves. We have a linear move, which would be in a what? It would be in a straight line. And then we have what we call a circular move, which moves in an arc. And those are 2 control path moves. And what happens is we'll say I want to go in this circle, or I want to go in this straight line, and then we say we want to move it at 100 millimeters per second. Well, it's trying to move it in a straight line, so what does that mean about each joint? Are they going to move at the same speed? When we say 100 millimeters per second, what do you think what are we trying to position? You're right, but what on the tool are we trying to position? The tool center point. So what we're trying to position is what we call the tool center point. So when I say 100 millimeters per second, the tool center point is going to move at 100 millimeters per second. But if I'm coming here trying to do a straight line, notice this axis is moving real fast. This axis right here is moving real slow. This axis right here is not hardly moving at all. So what happens on a control path move is we specify the tool at the center point, and then every axis runs at a speed to make it move in a control path, right? Does that make sense? So they're all running at different speeds, depending on where it's at in the move. And we have two control path moves. What do we call them? So the book's not right. It says always moves in a straight point between programming points. That is not true. We have two control path moves on all these robots. We have a linear move and we have a circular move. And we have one uncontrolled path move. Now, these are called joint moves. Kukla calls it a PTP. All the rest of them calls them joint moves. Here we go out and we teach a point and we say run all the motors at 100%. Well, if you say run all the motors at 100%, that means different axes are going to get to their final position at different times, which means the robot is going to follow an uncontrolled path. Now we called it an uncontrolled path, but once you see the path, it'll follow that path every time. But we don't know the path it's going to take the first time it does it, right? You understand? And that's the fastest we can move. So if I was trying to draw a straight line, I can't do it real fast. Why can't I do it real fast? Because my brain is trying to control the speed of all my axes to control a straight line. If I'm trying to do it as fast as I can possibly do it, there's no way in the world I can do a straight line. That's an uncontrolled path. So joint moves are the fastest the uncontrolled path is the fastest the robot will ever move. So normally we use non-controlled path moves for getting from up here. So we park the robot back up here, right? You understand that? To get it out of the way. And then we use uncontrolled path moves to get it down to the workpiece as fast as we possibly can. And then we switch over to the control path moves to actually control the path. The XY distance are different paths. It will form an angle, or it might form an arc, or it might form an S, or it might do something. But what you got to understand, once you do that control path moves, whatever path it follows when you run the program is the path it's going to follow in the teach mode. That's the path it's going to follow when we run the program. So they're showing this. Usually it's in an arc. So it follows different paths. So the book, for one thing, they're calling this a control path move, which would be true. But what's our other control path move? Yeah, we call it a circular, even though it doesn't do a circle. It would be more precisely called an arc move, but that's just the term they pick it up. In fact, to do a circle, we'd have to do two circular moves to do but this is control path. So that robot would actually come up here and follow this thing perfectly. It's not going to be a straight line. It's going to be something. Now, a robot, it depends on what axis and how far they got to go. So what happens on an uncontrolled path? We tell all the axes turn on at the same speed. Well, if this axis is set like this, and it's only got to go right there, and it's doing it, at 200 millimeters per second, it's going to get to this point before this guy gets to this point, which might be before that. Which means it's not going to follow a straight line. It's not going to follow. It's going to follow something, right? So you'll see it follow an S. Sometimes they'll do an S. Most of the time they do what we do. So normally when I'm trying to move between 2 points as fast as I possibly can, I usually go in an arc. If I'm up here, now down here I would go arc like that, but it's still not a controlled path. It's a path that, in other words, and these are the fastest moves. It's just like I said, to get from point A to point B, you're doing it as fast as you possibly can
you're not gonna do a straight line. So when you do a straight line, or even when you try to draw a perfect circle, what do you have to do? Yeah, now, and how fast are the axes moving? Well, out here, so when you set the speed out here. So I'm moving out here, but how fast is this move? My wrist is not changing at all, right? I'm not moving much back here. So what's happening is your controller's trying to do all this math to decide how fast and how fast to run each axis to cause that robot to move in an arc or to cause it to move in a straight line. So all of a sudden it's going to do what? It's going to slow down. But if we say follow an uncontrolled path move, then the controller just turns on all the motors at the same speed. So if I say 50%, it's going to turn them on at 50% speed. It's going to move. Different axes are going to get to different spots at the end point at different times, and it's going to follow an uncontrolled path, just like we do. Now what's neat is if I come up here and do this, every time I do this, I'm following basically a different path. So what we're saying is that once you see it do that first move, the path that it follows, that's the path it'll follow every time. So we can use this. So normally we use uncontrolled path moves to get the robot into position, and then we use control path moves while it works. We don't have very many. It's amazing to me. All these robots support 3 moves. You can do a linear, you can do a joint move, which is an uncontrolled path. You can do a linear move. You can do a circular move. Every one of them supports those 3. The Motoman supports what they call a spline move, which is it's a variation of circular move. So everything you see these point-to-point robots do, they're doing it with 3 moves. So we got 3 move instructions. That's all we got. If you understand those 3 move instructions, you got it down. If you use linear moves all the time, you're going to cycle. So if I'm trying to get my robot from a point to point without taking time, then joint moves are what you're going to do. You can see these programmers, they'll be out there, they'll be using linear moves all the time. What are they sacrificing? They're sacrificing what we call cycle time. Cycle time is production time, right? So that's one of the things they constantly do is try to trim the cycle time of the robot. For us, Steve Jobs, when they were putting out the first Lisa computer, way back there, he said, he was very concerned with the boot time of the robot. The boot time of a computer is how long it takes to load its operating. He said, these guys are going to use this from day in, day out, day in, day out. If you could trim 5 seconds off the boot time, you're going to be saving days off this person's use of that computer. So, you got Mercedes making 300,000 cars a year. They could trim 5 seconds off their cycle time. That's probably going to be almost 1,000 cars more that they can run by the end of the year, right? Cycle time is very important. You can see these programmers, they don't understand that. They don't understand trying to get that robot to move as fast as it possibly can when it can, right? You understand? And then slow it down to actually do the work. We'll show you that. Next class, what we'll do is we'll teach the program. We'll go over here on one of our robots. I'll teach the program, but you'll see what we're going to do and see a point-to-point robot. So the advantage of a point-to-point robot is that it's a lot simpler. It does probably 99% of the tasks that we needed to do. Some of those, so very seldom you're going to run into a continuous task. They are neat, right? We'll do that with the, all right guys. Sorry, usually on test day, we used to do a lecture day on test day. I know this is boring. No, I get boring.
I don't know it.
Oh, I would hate to use.
Thanks.
Yeah, wait. Morris has already got it. But it's online, so I'll send him an email. Here's the next combo drive right here.
Do we have to do that to you tomorrow
No,
on
this is-
Friday. You know, like, when I say video, I just mean like.
It would be on the calendar.
email with all
Except
the
this one.
quality.
This was down as being due today, but I forgot to give it to y'all. No, that's the homework lab.
I'm sure you said about 10 and 1 to 10. You want to see what's out there? Really good advice. You see West Side in the wild.
Is that a show? Is that a show?
Yeah.
Oh, the camera system.
It's a wild dog.
That's going on, there.
It's going to have a look. That's what the wild dog looks like. Think about that. Oh, they got. And what they do is they take the building, they put them out in the time where they got hard. Nothing there, right? Hey,
What do they call it? What Disney call it?
animatronics, that's what this is. But the reason they do it is to study the animals.
I guess they mount cameras and
You
stuff.
wonder, well, they got one, a prairie dog can jump and bark. Oh, they got a big, like, sea turtle. And you wonder if they're lifelike enough to convince the others. Those sea
Tried to
turtles,
mate with it or something.
so it mounted it.
That's what I was thinking, so I tried to mate with it.
Well, I thought it'd be a little bit different than what the real class is. No, I was asking you, when we made it.
No,
So,
no, I didn't give it out. And that was my fault. I had it ran off. I had it sitting here on my desk. I think I told y'all I was going to give it to you. If I
I'm gonna
remember.
hang on to it. Cool.
That's fine, but if you think you're going to lose it, just put it in that box up
Well,
there.
I'm gonna get it demonstrated.
Well, you can always put it, you can always get it back out, yeah. And that way you don't have to worry about keeping up with it, Jared.
You're not good.
Or just put it in the not ready to be graded box up there.
And about me missing today, I think I'm only gonna miss one day. But you'll have the recorded lectures. And I can.
I'll try. I really do. I really
Well,
do.
if you don't,
The,
hey, I'll just have to work through it.
in fact, I kept recording.